Alright, how about a very short video? That sounds good to me. The topic is heat flow, and in specific, it's the specific heat capacity. Here's a silly little demonstration I haven't done very often, but it's kind of interesting. You take two little paper cups, and you put one of them you fill with water. It's like a cone cup. Have you seen those? Before? Excuse me, itchy throat. In the other paper cup, you don't put anything. The right hand one has water in it. As the flame from beneath both of them begins, of course, the paper cup that has nothing in it begins to catch on fire right away. But the paper cup that has water in it, guess what? It doesn't catch on fire right away. Of course, if you continue to heat it pretty vigorously, it pushes it because the edges of the paper kind of get pretty hot. But the water absorbs a lot of that heat, preventing that paper cup from burning, at least right away. Water, I call water the champion of specific heat. It has at least approximately 4 or more times greater capacity to hold heat, or it also means it's harder to heat it up and harder to cool it off. That could be good, that could be bad. Generally, it's good. Thank goodness for that, because the oceans help serve as a blanket, keep the earth relatively warm at night and cool during the day. Different materials store different amounts of heat energy, in a sense, or perhaps I should say they not only store, but I clipped this off the internet. Maybe that's not so correct. Perhaps we should say different materials heat and cool differently. That's for sure. Storing heat energy, I don't know about that. Totally depends on how much you have and how well they give it up. Looks like gold heats and cools very quickly. This little match under the gold and the same match under the water. I think water, what's the specific heat capacity of gold? Let's go look. I wonder if I have it written down somewhere. 30 times longer. Interesting. Well, whatever. Let's go to 3 examples. This one looks like copper, Cu. This one looks like gold, Au. This one looks like glass. So here I have a certain mass, a certain object, 100 grams, 100 grams, 100 grams of each. But of course the glass heats and cools more easily than the gold. And the gold heats and cools more easily than the copper. And the copper heats and cools more easily than, well, let's wait and see the table. But in other words, if I added 1 joule of energy to this one, 1 joule of energy to this one, 1 joule of energy to this one, which one would warm up the most? And the answer is the glass would, because it heats and it responds to heating and cooling much more quickly. Another way to say it is the heat capacity, the specific heat capacity, is the amount of heat necessary to raise 1 gram of substance 1 degree Celsius. So if I had 1 gram and I wanted to warm it up 1 degree Celsius, it would take 0.385 joules of energy. If I have 100 grams and I want to warm it up 1 degree Celsius, well, try 100 times that much. So if I had 100 grams of copper, I can imagine that, maybe you can imagine that, and I wanted to warm it up 1 degree Celsius, that would take 385 joules of energy, or 0.385 kilojoules. It would take less energy than that to warm up the gold, and even less energy than that to warm up the glass. Interesting. So the smaller the heat capacity, which is the amount of heat required to warm up 1 gram of substance by 1 degree Celsius, the larger the heat capacity, the slower it responds to heating and cooling. The smaller the heat capacity, the more quickly it responds to heating and cooling. I call water the champion of specific heat. Look at all these. These are like less than 1. But water has a number 4, more than 4 joules per gram degree Celsius. So to warm up 1 gram of water, 1 degree Celsius would be 4.18 joules. To warm up 100 grams of water, 100 grams of water by 1 degree Celsius would take... Oh, did I say that wrong earlier? I moved that decimal too far last time. So if I had 100 grams of copper, to warm up 1 degree Celsius, it would take 38.5 joules. There we go, I said it right that time. Similarly, if I had 100 grams of water, 100 milliliters of water, I wanted to warm it up 1 degree Celsius, that would take 418 joules. Interesting. Here's a table. It's not a complete table. There are much more complete tables than this. Wood, glass, ice. Ice is similar, not similar, but it's, of course, made of water, but the water molecules being freed up to move around in liquid attain even a higher heat capacity. Look at air. Is air a good insulator, a good thermal insulator? And the answer is yeah. But water's even better. Water's a better thermal insulator. Water or air could serve as a blanket to prevent heating and cooling. Here's the equation. We've seen it before, perhaps. We'll see it again in, golly, chapter 10, I believe, but who cares what chapter it is? It's the heat. I call it the heat equation. The heat flow is equal to the mass of the sample in grams times the specific heat or specific heat capacity I prefer it joules per gram degree Celsius, and the Celsius comes in right here with the temperature, ending minus beginning. So what if I had a chunk of iron, 10 grams of iron, 10 grams of water, 10 grams of glass? Iron has this specific heat, water specific heat, glass specific heat, 1 degree Celsius. Looks like it would take 4.5 joules to warm up that 10 grams of iron, 1 degree Celsius. 41, almost 42 joules for the water, and a little bit less than 2 joules for the glass. So if I were going with iron, water, and glass, which of these curves is which? Let's see, water responds the slowest to heating and cooling, so I'm going to go with this one being water. Hey, what's happening here where it flattens out? Oh, I know what happens to water at 100 degrees Celsius. Boiling. And let's see, comparing iron and glass, iron is a larger number. Oh, wait. Yeah, true. Iron is a larger specific heat than glass by at least 2 times. So is it true that iron would warm up more slowly than glass? So this must be the iron, this must be the water, that must be the glass. Glass responds quickly to heating and cooling. And similarly, if I had wood, iron, air, water responds the slowest heating capacity as the largest heating, specific heat. It responds the slowest heating and cooling, followed by air, followed by iron, followed by wood, although you can fill in the blanks in between those with any substances that have appropriate specific heats. Interesting. Or what if I'm cooling things off? Does it work the same way? Similarly, right? Looks like water would cool the slowest. Iron would cool faster. Air would cool... Oh no! Did I screw that up? I might have. Iron and air. I think air has a bigger heat capacity than iron. I drew that correctly here. Water, air, iron. Dang, I screwed that up. Alright, I gotta fix that before I post this PDF. But if you're watching this video, listening to my adorable voice, getting bored to tears, you know that I made a mistake here, and I'll switch that on the PDF. Snap. Because water is in a good place, but air responds more slowly to heating and cooling than iron. So these two, if I could switch the word air and iron, I'll be good. And wood? Better check that. What about wood? Does wood have a lower heat capacity than iron, meaning it cools more quickly than iron? And how does it compare to air? It goes water, air, iron, wood. Water, air, iron, wood. What is the heat capacity for wood? Sorry to waste your time here. I'm going to check. Okay. Sure enough, there it is. Alright, fine. I was not wrong there, but I am wrong. I need to switch these two words right here. In any case, I'll switch them on the PDF. Thanks for watching, guys. I said this was a short video. I gotta shut up. Bye!